Hi guys, this is Dr. J, and in this video I'm going to introduce for you our section on electromagnetic or EM survey methods. And this is covering chapters 10, 11, and 12 in the textbook. Now EM is a very broad category of surveying methods, and it spans a whole range of different frequencies and different types of instruments and different applications. So we're going to be surveying those different applications in this module a little bit, but I wanted to take just a few minutes here at the beginning to give you an introduction to the basics of how the method works, what kinds of things are we measuring when we do this type of surveying, and give you a little bit of that background. So first of all, EM surveying is based on the physics of how electromagnetic radiation works, and especially how electric and magnetic fields stimulate or create one another. And sorry I don't have this marked on here, but this is basically based on Maxwell's equations. And you've all had physics, I'm sure. Some of you may have had advanced physics classes in electromagnetics or quantum mechanics, and so you've probably seen these equations before. Probably you tried to forget them, but these are very important for how EM surveying works. And so the basics here, and I'm not going to go into a lot of details of the math, but the basics here is that B is our magnetic field, E is an electric field, J is electrical current density. You can think about this as just electrons per some unit area. And what these equations say is that the curl, del cross B, the curl of the magnetic field is related to the electric field and the current density. And the curl of the electric field is related to the negative time derivative of the magnetic field. And sorry, I should have said that the curl of the magnetic field is related to the time derivative of the electric field. Basically what this means, if we can put this in simple language for a minute, is that if we put a current through a wire, that current is automatically going to generate a magnetic field. And if we have a magnetic field, that magnetic field is going to generate electrical currents in conductors. So there's this back and forth, they go one with the other. And I have another video posted from a YouTube channel called Crash Course, where they go into this concept in much more detail. A magnetic field induces an electric field, which induces a magnetic field, and so on and so forth. Now I have here in these two diagrams, the smaller one in color and the larger one in black and white, I just wanted to give you guys two different perspectives. They're basically showing the same thing, but this is essentially what we're doing in EM surveying. Now this is a little bit application specific because we're showing here an actual loop, and in some types of EM surveying you're actually using natural fields or fields which are generated by very far field sources. And we'll talk about those in more detail in another video. But basic concept, you have a loop of wire, you put a current through that wire, and that generates these magnetic field lines, which you can see, as a result of that electric field. A loop of wire carrying a current, that induces a magnetic field. Primary magnetic field lines. Now if you intersect a conductor, as they're showing here, and in this case here as well, if you intersect that conductor, that magnetic field, as we said, it induces an electric field. Again, if you're inducing an electric current, an eddy current in this target, this conductive body, those are going to generate secondary magnetic fields. And you can see those in the dashed arrows. So we're generating an electric current, which generates a magnetic field around those currents, which generates electrical currents in the body that we're targeting from those magnetic fields that we've generated from this current, and those electrical currents in the body, in the target, in that conductive body in the subsurface, are going to generate secondary magnetic fields. And then, so we're generating all these things, and then we receive them, so we have a second antenna to measure the signal, and we know, because we're transmitting, we know what the signal is from the transmitter, or in the case of tellurics or very long, low frequency, long wavelength sources, we generally know what the characteristics are of the source. We can essentially, at the antenna or at the receiver, we remove the effect of the transmitter, we remove the effect of the primary fields, and that gives us the secondary fields. And basically what it is, it's a phase shift. And the book talks about this quite a bit in some detail in the sections that you're going to read. So basically we have a phase shift from the current in the primary field, or I should say from the magnetic field induced by the current in the transmitter loop, or again in the case of very low frequency methods, we'll know something about the characteristics of that. Either way, we'll know something about the characteristics of the source of that magnetic field, which has induced the electrical currents in the body, in the subsurface, and then we can remove that or account for that and then measure what the effect is of these secondary magnetic fields. Make sense? So we start at the transmitter, we know what that is, we're inducing magnetic fields, which are inducing electric fields, which are inducing magnetic fields, and then because of the fact that we know what the transmitter is doing, we can subtract out that effect or account for that effect, and basically measure a phase shift which is associated with these secondary magnetic currents, and that gives us the information on this conductive body. Okay, so that's the basic, at a very high level, that's kind of understanding how the EM method works. Now, I said it was a phase shift, and a phase shift implies a wave, and in fact these are electromagnetic methods, so you can think of an electromagnetic wave which has a frequency and a wavelength and so forth, and there are different methods that work at different frequencies. We have resistivity, and again this is just a constant DC current, there's no frequency component to the current, as opposed to AC, alternating current, which does have a frequency component. So self-potential, magnetic resistivity, those are going to be very low methods. Induced potential, those again very low frequency. EM induction, we're getting into these more moderate high frequencies. GPR, which we talked about last week, those are even higher frequencies yet. And actually there's, so this is on a log scale, so actually there's no really 0 point on this scale. It goes negative for negative powers. So this is 1, 10, 100, and so forth. For negative frequencies, you'll have 10 to the minus 1, 10 to the minus 2, and so forth. So at those very, very low frequencies, that's where we get the magnetotelluric methods and the VLF methods. And those, again, we'll be going over those later on. But okay, so this is the foundation for what we're talking about in this module. These electrical fields, which are generating magnetic fields, which are generating electrical fields, which are generating magnetic fields, which again generate electrical fields in our receiver, and which we measure and are able to then relate back to our transmitted signal and account for that, and then figure out what the signal coming from the target body is like, and then we're using that to estimate conductivity and so forth, resistivity in the subsurface. So that's a very high level overview, and in the next video we'll talk in more details about how that works for some particular methods.